Hello, everyone. Welcome to this online lecture on the bond and development lens. As the title implies, that without considering these two factors, bond and development lens in steel reinforcement in beams, the steel will actually be useless. And that's what we're going to discuss and elaborate upon in this video. At the end of this lecture, I will offer some multiple choice questions for you to test your knowledge. Bond and development length. We will learn what is bond stress, what is bond failure, what is the development length, what do we mean by development here. So let me first give you some background on how the reinforcing bars look like in the longitudinal direction. Any reinforcing bar would have these kind of deformations over the surface of the bar. These deformations, we call them uh, reinforcing bar rips or lugs. Okay, the benefit of these rips over the bar is to make it difficult for the bar to slip under the effect of the force that would be tension or compression. We'll focus on tension force for now because we understand that reinforcement is the element that carries tension on behalf of concrete that is actually lacking the ability of resisting tension. When this happens, there will be some sort of bearing forces generated at the interface between the bar and the surrounding concrete, ensuring that the bar is not going anywhere under the tension force, right? And therefore it will not pull out of the concrete or will not slip off the concrete. This is one measure we do and we make sure, and it's now implemented in the codes of practice, that smooth bars without deformation or rips aren't allowed. But there are other factors that we need also take into consideration, like development length. To demonstrate the development length in an element like this beam here, think of this beam as an element that you just designed and you evaluated the bending moment diagram for this beam, which is in fact connected to a stronger element, that this element which can be a strong column or a wall, a shear wall, concrete wall. And we can easily identify this system to look like this cantilever. We understand that the bending moment at the connection between the beam and the wall is actually fixed. Due to the fixation here is actually negative bending moment, which is this here, negative bending moment, that would require reinforcement at the tension, which is the top of the concrete. So when designing this section here, we make sure that we provide the reinforcement needed to resist M negative here. All right, so what's the difference between the beam 1 on the right side of the screen and 2 on the left side of the screen? You notice that the reinforcement on the right side of the concrete beam is extended inside the column or inside the wall to a distance equal LD. LD is the development length. This extension is not here in the beam on the left side. The bars extended into the support, that is a wall or a column, for a distance LD here ensures that they are useful and they will be doing the job they intended to, which is resisting that moment and therefore the tension force generated in the bars at this location. They will not act this way if we do not extend the bars inside. Think of a real life application that you would like to hang a frame on the wall like this. Why do you have to insert the bolt inside the wall into a specific distance inside the wall? Why don't you just have it superficially uh, located in the wall, because the weight of the frame will pull down that bolt from the wall, and the bolt will easily pull out the wall. In a similar sense, you need, for any object or any bar that's subjected to tension, for it to be able to carry that tension force, is to extend the bar inside the element it supports it. That extension is called development length. Very good. Now, we can now understand that the tension force in the bar, to be able to transfer from the bar to the concrete, it would be done if we have enough bond stress between the bar and the concrete. And this bond is guaranteed by extending the bars inside the concrete a certain distance. That distance over which the transfer from the bar to the concrete takes place is called development length. To evaluate the development length in tension, we need to apply in that equation. That equation, it might look complicated, but it is easier than you think. For a certain reason, that most of these factors are very easy to obtain and they have significance. Also, the resulting value of LD would be a function of dB, which is like a number multiplied by dB, so that we come up with saying the tension development length is a number times dB, like 60 dB, 70 dB, and so on. And the equation is here indicates that the development length depends on some characteristics that we might already know. It depends on the yield stress of steel, concrete compressive strength, and it depends on a bunch of psi factors and the lambda and this factor here. Okay, if we go quickly through these values here, you see that the development length is affected by the reinforcement location represented by this factor psi t, and is also dependent on whether we have epoxy coating on the bar or not. That's represented using psi e. It also dependent on the size of the bar itself. Is it a big bar or is it a small bar in terms of bar diameter through factor psi s? These are all factors related to the steel reinforcement denominator of the equation here. In the denominator, there is another factor that is related to concrete, which is lambda, and it's the lightweight concrete effect. And there is also a factor here between these brackets that takes into consideration the spacing between the bars and the cover also, uh, between the bar and the bottom surface, top surface, and side surface of the concrete, in addition to the presence of the transverse reinforcement. The transverse reinforcement here is the stirrups. So, what are the characteristics? How the stirrups characteristics affect the evaluation of LT? So let's go factor by factor here. We'll start by psi t, which is the reinforcement location factor. It is, according to the code, bottom bars would not require a change in the bond length or development length. However, top bars, we need to increase the bond length for them or the development length for them. But why? What is the rationale behind this? Think of a concrete section like this at the time of placing the concrete. We have already these bottom bars. You keep pouring concrete here, and therefore concrete around this is very condensed compared to bars on top. Because as we keep condensing concrete when we're placing them, perhaps there will be some settlements underneath the top bars. With time, the concrete as a in its fresh state will actually settle, leaving some air next to the bars. This would make the concrete around the bar on top loose, and therefore they will not bond as well as concrete with the steel bars at the bottom. For that reason, for top bars, we use epsilon or in a way that we increase the development length by 1.3. What is that distance that we should consider as top bars? 300 millimeter. So if we have a distance less than 300 millimeter, we deal with them as uh, regular bottom bars. But as you know, that uh, this height is rare to be less than 300, and therefore, in a rule of thumb, that for bottom bars we use epsilon t equal 1. For top bars we use epsilon t equals 1.3. Another factor is the bar coating factor, epsilon E for epoxy. We sometimes need to coat the bars with epoxy to prevent corrosion. Epoxy is elastic type material when hardens and it is smooth, making the surface of the bar smoother, and therefore it would negatively affect the bond, and therefore we need to increase the development length if we use epoxy coating. Epoxy coating is not used in everywhere, of course. It is used in primarily cold countries where we're afraid of corrosion, and therefore psi E should be taken into consideration, should take into consideration this fact and increase the development length by 1.5. That's of course in case the clear spacing is less than 6 dB and the cover is less than 3 dB. These conditions are easily satisfied, and I would guarantee that psi E would be taken of 1.5 in case it's epoxy coated. But in other cases, if this condition is not satisfied, which is rare, psi E then would be equal to 1.2. For uncoated bars, like the ones used in Gulf countries, psi E would equal to 1 because it's not epoxy coated in general. Well, there is another condition that psi T times psi E need not to be taken larger than 1.7. So in case you evaluated psi T, which is a bar location as factor, and psi E, which is a bar coating factor, and the result was greater than 1.7, you should take it as 1.7. The other factor, which is the reinforcement bar factor, psi S. Now, I'd like just to think together here. Suppose that based on your design, you came up with a design that you need area of steel. Area of steel can be 4 bars of a certain bar diameter, dB1, or it can be just here with me, or equal to 2 bar diameters only of diameter, bigger bar diameter of dB2. In fact, this and this, they both have the same area AS, all right? The selection of 4 bars of bar diameter dB1 has an area of AS, and the selection of 2 bars of bigger bar diameter dB2 has also AS. So in terms of design, we're using the same area approximately. But which selection is better in terms of bond? The first selection is better in terms of bond. Why? Because the surface area of a bar, which is the perimeter multiplied by the length, for the case of smaller bar diameter, is bigger than that of the surface area of a larger bar diameter. Surface area is means what? It's a contact area between the bars and the concrete. More contact area means better bond. And that's why if we're using bigger bars, the code says uh, number 19 and more, that's the threshold. If we're using number 19 bars and less, we use psi s equal to 0.8. But number 19 millimeter bars excluded, so more than number 19 millimeter bars and above, psi s will be equal to 1. The effect of lightweight concrete, lambda. Intuitively, when we think of lightweight concrete, it has less contact with the reinforcement than denser concrete or normal weight concrete. For that reason, when we have lightweight concrete, which means essentially utilizing lightweight aggregate, then we use lambda equal to 0.75. If we use coarse aggregate, like the one we use for normal concrete, but we use sand, which is fine aggregate that is lightweight, then we use lambda something in between, which is 0.85. Of course, this information should be known for the project you're working with, and therefore you will be able to select properly the value for lambda. Now, let's talk about the effect of spacing and cover, all combined in one factor that we refer to as the confinement effect. Let's look in detail what's inside these brackets and which factor is related to what. First, CB. CB actually is the cover or the spacing between bars. In fact, one one thing you need to remember that we always keep maintaining uh, a value for the cover, which is a distance from the center line of the bar to the concrete surface, right? This cover not only the cover on from the bar to the bottom or top concrete surface, but also to the side. All right. So this can be one value for CB, and this is another value for CB. Also, the spacing between the bars divided by 2 is another value of CB3, which is S over 3. When selecting the value for CB to be located in the equation, we select the smallest among the three values. It's very important to maintain these values as per the code represented in other provisions, like, for example, the necessity for making sure the concrete cover is 38 millimeter for beams, 40 millimeter for columns. Also, remember when we selected the minimum, it was for this reason as well, not only for making sure the concrete we pour would reach the bottom, but also because when having the steel bars very close to each other, concrete in between tend to split, making sure, and when concrete between the bars split, it would reduce the bond between the bars and the concrete. All right, so this is for CB. Other factor is KTR. KTR is that factor that appears in the confinement effect factor, and KTR takes into consideration the characteristic of the stirrups. KTR is the factor related to the transverse reinforcement. The transverse reinforcement is in basically the stirrups in bars or ties in columns. KTR is equal to the area of the transverse reinforcement, okay, the area of the stirrup, one stirrup, or the area of the one tie in columns, multiplied by F yield of the transverse reinforcement, which is usually 420 MPa, divided by 10 multiplied by S, and S here is the center to center spacing of the transverse reinforcement, which is spacing between stirrups or spacing between ties, according, of course, to the code provisions for this or that. And N is the number of bars, total number of bars to be developed, which in a case of a beam, for example, if we have here 4 bars or these 4 bars, so n here is equal to 4 because these are the bars that we need to develop. All right, there is one condition here that after evaluating CB and KTR over DB, which is a confinement effect, if its value is greater than 2.5, we are not allowed to use this value for more than 2.5. Let's look at an example here, and this example it demonstrates how to evaluate development length for a beam. Okay, this beam here given with full information, and notably you can see that the side cover, the lower cover, the spacing, they are all 80 millimeter. We will use this. We also have information about the stirrups. Okay, here I'd like just to remind you with the equation that we need to use. So we need basically for the case we have in this example to evaluate psi t, psi e, psi s, right? And lambda for the case we have. And remember that we're talking, of course, about here epoxy coated bars, and obviously they are bottom bars. Given Fc prime, F yield, we'd like to solve this problem assuming KTR, which we already have seen in the confinement effect, equal to zero. This is where the characteristics of stirrups comes to play. Uh, it's like assuming it's zero. It's lazy engineers decided not to take it into consideration, so select it as zero. Or that we evaluate KTR so that we see the difference when we consider the characteristics of stirrups versus not considering the characteristics of the stirrups. All right, so let's evaluate the different factors. Psi t, we're talking about bottom bars, and therefore psi t is equal to 1. Psi e, we're talking about epoxy coated, and the clear spacing represents 6 dB, so it's 1.5. The multiplication of psi t and psi e is 1.5, which is 1.7, which is okay. The effect of bar diameter or bar size and lambda are equal to 1 because we're talking about bar diameter number 25, which is greater than 19. This means psi s is equal to 1. And lambda, we're talking about normal weight concrete. That's why lambda is equal to 1. CB is evaluated as we have seen before. That would be either the, the cover, side cover and bottom cover, they both eat 80 millimeter, or the spacing center to center of the bars. We are talking about spacing of 80 divided by 2. So this gives us 40. We need to select the lower value, which is 40 millimeter for CB, which controls CB value. Now, if we would like to evaluate LD, the development length, considering KTR in the confinement effect factor equals to 0, we would evaluate the confinement effect factor as CB, which is we evaluate as 40, plus 0, which is KTR, divided by 25.4, that's the bar diameter. It's okay for me that you use dB equal 25. 25.4 is more accurate because it is the actual bar diameter versus 25, which is a nominal bar diameter or designated bar diameter. With this confinement effect factor is equal to 1.575. That's less than 2.5, which is okay. From this, we implement the equation. After knowing all the values we already obtained, we would evaluate LD as a function of dB. LD would over dB as a ratio, we get a number that's 9 over 10 multiplied by F yield, which is 420 MPa, divided by lambda, which is 1, square root of Fc prime, which is 21 MPa, psi t 1, psi e 1.5, psi s 1, divided by the confinement factor, which is 1.575. That gives us a value of 78.6, which means LD is equal to 78.6 dB. B in the question is to evaluate the same value, but after considering the actual value of KTR. KTR is equal to 42 ATR over SN, and 42 is actually F yield T divided by 10, which is 420 divided by 10, which is 42, multiplied by ATR over SN. ATR is the cross-sectional area of the transverse reinforcement. We're talking about one stirrup like that, cut here and here. So we are talking about bar diameter 10 area, which is 71 millimeter square, times 2, divided by S, which is the spacing between the stirrups, which is given as 200 millimeter, multiplied by the number of longitudinal bars. We have already 4 bars, so the number N equals 4. This gives us KTR a value of 7.45 millimeter. Remember that this is a dimensional quantity. With this, the confinement factor would equal to 40 plus 7.45 over dB, that's 1.87, still less than 2.5. From this, we evaluate an updated value of LD that is equal to 66.2 dB. Well, if you are asked by someone what would be the development length for steel bars in tension, and you don't want to go through all of this, you can safely say 70 to 80 dB based on this example, which is practical, which is like any uh, different beams that you can see in real life. Bars in columns are also developed, and because they are subjected to compression, there is also another equation that we use for evaluating the development length in compression. And in the development length in compression doesn't require as many parameters as that used for tension development length. And the equation of the ACI code is pretty simpler, in which we apply in this equation here that LDC development length in compression is equal to zero point zero 0.02 F yield dB divided by lambda square root of FC prime. This means that the development length in compression is only a function of the material characteristics of steel and concrete and the bar diameter, in addition to whether we're using lightweight concrete or normal weight concrete. After we evaluate this value, we need to compare it with our threshold here, that is this value of 0.003 F yield dB. So if we evaluate the first term here and it was less than uh, this term, we need to use this term. Under any circumstances, we are not allowed to provide development length in compression that is, in fact, less than 200. Well, here is the time for testing our knowledge through some multiple choice questions. Please feel free to pause anytime so that you would have time to think of the answer. For question number one, it says, what is the primary purpose of tension development length in reinforced concrete? And the answer is A, to ensure that the reinforcing bar develops its full tensile strength before being terminated. Question number two, what is the main function of the deformation, which is rips or lugs, on steel bars in reinforced concrete? And the answer is to enhance the bond strength and reduce slippage. Question number three, why do epoxy coated reinforcing bars require increased development length? And the answer is B. They have reduced bond strength with concrete because they are, of course, smoother than the original bars. Question number four. Compared to larger bars, why do smaller reinforcing bars require shorter development length? And the answer is they have a greater surface area relative to their volume. Question number five. What is the impact of using lightweight concrete aggregate on development length? And the answer is it increases the development length. And that's obvious because a lightweight aggregate concrete has less bond. Question number six, which is the last one. What is a likely outcome if the detailing of reinforcement in concrete doesn't ensure full bond between concrete and steel? And the answer is reduced effectiveness and potential failure. Which concludes our lecture today. Please leave a comment in case you have any question, and I'll be glad to answer you. Thank you.